Is the screen visible?
Yes, sir, it is. Yeah.
Okay. Okay. This is going to be really kind of a compressed capsule, like which I'm going to do in the next 90 minutes or 80-85 minutes. I'll try and give you just the gist of, I think, what I want you to know at this point of time. Okay, I think the question that I asked you in the uh, assignment, which I backtracked and then retracted and then gave you a simpler one, was this question. Suppose if I take a mixture of WF6 and WCl6 and then shake it together, I think I'll get an equilibration giving rise to these, six, possibilities, or more than 7 possibilities, rather, or 9 possibilities, right? 9 possibilities, because some of them are isomers also, right? So you have a monochloro, dichloro trans, dichloro cis, trichloro, meridional, facial, tetrachloro, and the 2 isomers cis and trans, and then the pentachloro. Okay, so these are the possible isomers. So in fact, this particular reaction, I think, gets mentioned in most of the textbooks and lectures and tutorials and all possible places, because this reaction does really take place. It's not an hypothetical reaction. The reaction does take place. But I'm going to come back to this towards, I think, just after 2/3 of the lecture is over, I'll just come back and then solve this problem. Before that, let me just quickly give you an overview or important points about heteronuclear NMR. Okay. I think 1H and 13C have been taught quite well for you, okay, in the first half of the course. So let's worry a little bit about this other non-protic and non-carbon NMR spectrum. This is just kind of table I extracted from the book, same book. I think this is by Ebsworth Rankin book. I think there are two important parameters you have to look at whenever you're talking about NMR. One is the natural abundance, other one is the receptivity or sensitivity. Different books use different terms, which is a comparative or a relative term, actually. In this table, I'm only dealing with I is equal to half nuclei. I is equal to half nuclei are the ones which are non-quadrupolar. There is no line broadening problems. So what I have listed here is some of the I is equal to half nuclei. If you look at the first in the list, namely proton or 1H NMR, it has almost 100% abundance. The natural abundance of 1H, subtracting the abundance of deuterium and tritium, tritium is about 19.85, it's almost like 100%. And the receptivity of this is considered as the baseline. That's the kind of the, related to this only we describe the rest. If something is having 100% abundance and the receptivity as close as possible to 1.0, that means these nuclei are highly amenable for being studied by NMR spectroscopy. Just there are 3 examples here, 3 entries here, which I've shaded with the yellow. All 3 of them have 100% abundance. All 3 of them, but not all 3 of them have the same amount of sensitivity. You see that fluorine NMR has, that is 0.83. I think 8.3 in 10 to the minus 1 is nothing but 0.83. 0.83 is something that as close as you can get to 1.0. So fluorine NMR is as good as proton NMR in terms of the ease of getting a good spectrum. You have a compound, you have a few milligrams, put in the NMR tube. It is assumed that it has got proton, phosphorus, fluorine, and some other nuclei. Within a few scans, you can get proton spectrum and fluorine spectrum, because they have almost close to 100% receptive, 100% abundance, and almost 1 as the sensitivity or receptivity. Phosphorus is still good. It has 100% abundance. It's about 0.06 is the receptivity, okay, because it's 10 to the minus 2 of minus 0.07, I would write. Okay, it's not too bad, but you need to run the spectrum a little longer. You have to collect more data to see the signals of phosphorus. And you come to the other yellow shaded one, namely the rhodium 103. Rhodium 103 has 100% abundance, but has a receptivity of 3.2 into 10 power minus 5. Okay, that's 0.00032. I think that's the receptivity. So as you can see, uh, of course, I mean these are important, but I'm not going to talk about this today. I'm only talking about the two columns, namely abundance and this. So, but there are also nuclei which are important in terms of a chemical sense. Okay, for most organic compounds have carbon and nitrogen. Okay, N14 is quadrupolar. I is greater than half. So that is the most abundant isotope. That's of no use. But there's one isotope, namely 15 nitrogen, which has a very small abundance, about 0.37, less than a percent. But it is I is equal to half, non-quadrupolar, gives rise to signals. Although the receptivity is somewhat poor, this is an important nucleus. Again, carbon. Receptivity is poor, but the abundance is also poor. But all organic compounds have carbon and hydrogen, so we cannot do away with the carbon. So that's why carbon NMR spectra are run overnight for many dilute samples. You have to collect more and more FIDs to process to get a reasonable spectrum. So essentially, it's a compromise between the abundance, receptivity, and also the chemical sense. You know, I mean, like how much some. See, for example, here there is another one called 109 silver. Okay, it has a fairly high abundance, 50% abundant it is, and not very bad receptivity, but still you do not, it does not make sense how much of silver compound you will be synthesizing or will be interested in terms of biology or material science for you to go and do this. So essentially the NMR spectroscopy revolves around I is equal to half nuclei, you got sharp lines, okay. As I said, there also you can do NMR for elements like 109 silver. There are other problems which I have not talked about before. I talked about tau. So, okay, the tau here is 1000 seconds. This is too sluggish. It does not relax at all. Even these are problematic systems. Okay, again, just for information, I'm not going to really dwell too much upon that. I'm having a part 2 of the table again to bring in a few important nuclei or isotopes which are of immense importance or utility to inorganic chemists, especially when it comes to biology or material science. But are catalysis. Tungsten and platinum are, as you know, two elements which are often used as shock type of catalyst, shock metathesis catalyst made up of molybdenum tungsten. Same way, lots of platinum-based molecules in biology as well as in material science and catalysis like cisplatin and platinum-based carbonyl compounds and so on and so forth. These are of high interest. They have fairly good abundance and not so very bad, but not so very bad receptivities. So these are the nucleus which keep coming again and again when you talk about structural elucidation using NMR spectroscopy for inorganic compounds. If move on to I is not equal to half, this is again I is equal to half system. If you move to I is equal to not equal systems, before that, let me just talk about the 4 important points. I think I already talked about. One is isotopic abundance, sensitivity, and third is quadruple. I mean, okay, the quadruple ones are not so very great. Okay, when spin is greater than I is equal to half, then you have this quadrupolar movement usually larger, and the line widths become excessively large. And the relaxation time I talked about in the very first lecture I gave you. Okay. So now, the nuclei which possess a quadruple moment, quadruple is nothing but you don't have spherical symmetry. Okay, for the charges. Okay, the charge distribution is now elliptical. So a quadruple is the right term. I mean, I can say cruelly as elliptical. So it's far from the spherical symmetry. As a result, the relaxation times become very short, and then instead of 0 to 10 hertz, a few hertz, I would say, as the W off for I is equal to half. For I is greater than half, it can go up to 50 kilohertz. That means the spectrum will be more like a road hump. Okay. Okay. However, I think this is a point I think I must tell you, although I'm not dwelling too much on the quadrupolar NMR spectroscopy. Narrow lines can, however, be obtained for low molecular weight molecules if the quadrupolar nuclei is embedded in a ligand field which is highly symmetric. Suppose I have a symmetric field such as this. Okay, I think these are my ligands. and this is my quadrupolar nuclei. For example, let me talk about lithium. Lithium 7 is a quadrupolar nuclei. Or I talk about a very common anion which all of us use, sodium borohydride or lithium borohydride, where boron 10 or boron 11, both are quadrupolar nucleus. So these are in symmetric fields. This is a tetrahedral field. This is an OH field or a cubic field, or could be an octahedral field also. Okay, whenever you have a quadrupolar nuclei in the middle of a symmetric field, okay, this quarter, because there's a very spherical field around it, the quadrupolar moment of this gets somewhat cancelled. As a result, you can see fairly sharp signals. This is a point which I'm going to talk about towards the end of this lecture. Okay, I will talk about especially this example of sodium borohydride and show you how one can record a proton NMR where the 11 boron or 10 boron can couple and give rise to a multiplet. I will come to that. Okay. So just again a table, just to give an idea about some of the quadrupolar nuclei. Okay, I just highlighted only one. I may not go beyond this. 10 boron, 11 boron. One as I is equal to 3. The other as I is equal to 3 by 2. Very nice abundance. I is equal to 3 by 2, which is 11 boron has the abundance of 80%, almost 4/5. This is 1/5. Okay. Of the total abundance, as you can see, boron 10, boron 11 constitute the total 100%, and receptivity is not too bad, 10 per minus 2. Okay, that's not at all bad actually. Okay, so as a result, you can do boron NMR, and boron also is a very important element in biology. Especially boron capture therapy for cancer cure and other things. The boranes and the carboranes in many fields, okay, in material science as well as in biology. So boron NMR becomes very useful, especially in the field of biology and medicine. Okay. Another example I'm not highlighted, but equally important is because I did this for you guys in 438, CH438 last semester when I taught about organolithium salts, methyl lithium, beta lithium. So I'm not talking about it in today's lecture. So one has 92.6, other one got 7.4. So I is equal to 1, I is equal to 3 by 2, 1.5. So one has a very good receptivity, other one is not so good. But again, lithium 7 NMR is fairly common. Okay. So this is an overview of what I gave you. Okay. And there are other quadrupolar nuclei where quadruple moment in a I can vary from 1 to 5. I think there's also one nice example which is not here in this table is germanium can have I value of 9 by 2. That's 4.5. Okay, that's probably the highest I think among whatever you have here. Okay. Okay.
Sir,
Yes.
sir, what do you mean by negative relative receptivity? When it is negative, that means?
Say it again. Oh, sorry.
So, like for lithium and all, they have relative receptivity negative. So, negative
It's
means
not
a
negative.
large
It's not negative.
characteristic.
No, it's not negative. Not negative. It's 0.001 or 0.0003. Okay, 1.3 in 10 power minus 1 is nothing but, how do you write this? 0.013. And this is 0.0039. I'm missing 10. No, this is 0.13. This is correct. This is 0.13. This is 0.0039. This is not 0. Okay, it is still positive.
Okay.
Yeah, very small number. Okay, there's okay.
But at the same time, we are seeing negative quadruple moment. That is possible, right?
The quadruple negative is possible. I mean,
Okay.
see, that's essentially the quadruple or the ellipsoids shape. Okay, that's what it signifies. The positive and negative sign. Okay, I don't want to take lecture on today on quadruple quadruple moment. I think probably this has been taught in 101 physical chemistry. Has it been or not? Should have been taught. What is the dipole? What is the quadrupole? Right? I think it's been taught. So I assume it has been taught. I think that's not in today's syllabus, definitely. Okay. So only just think that instead of spherical symmetry, you have a non-spherical symmetry. As a result, the dissipation is fast. As the dissipation is fast, the relax is very fast. So tau is small. As a result, lines are broad. I think that's all you have to remember. Okay. Is this clear right now? I think the two points I really worry about is that the NMR active nucleus should have a fairly good abundance, like fluorine, like phosphorus, like rhodium, like proton. Okay, and if it has a good sensitivity, is very good. If the sensitivity is bad, it's okay. Then you can run the spectrum for too long. But there are also nuclei like carbon and 15 nitrogen and some other elements, what I showed in the previous slide, like even 57 iron. Okay, so these are low abundant ones, but this may be of interest to us, so we run spectra a little longer. Okay, so this is kind of summarized. I give you the slides, you can go through this yourself. This is all essentially taken from Rankin's book. I think the Rankin book is available freely for downloading from lots of sites. Okay, so you can download and have a look at it. Okay, so I think that's pretty much the introduction I wanted to give before I start solving some problems. Uh, so the notable nuclei I think are 19F. This is both in organic and inorganic chemistry. I think both of us are interested. Both the disciplines are interested in fluorine NMR because organofluorine and inorganic fluorine compounds are of immense interest. Same thing about 29 silicon. Silicon NMR is important for both inorganic as well as organic. In the organic side is polymers, silane polymers. Okay, in the inorganic side it's the silicates and zeolites. Okay, so it's of interest. 31 PNMR again is of interest to both medicinal chemists, bioorganic chemists, and the coordination chemists because phosphine complexes are of importance in metal carbonyl chemistry. A couple of examples I'll talk about it today. Okay, so as you can see, they're all fairly good, 100% abundance. Okay, sensitivity is 0.83. Okay, so you can for this fluorine. This is for silicon, somewhat low abundance, but not so very bad sensitivity. 31 phosphorus, very high abundance, not very bad sensitivity. So these are some of the common ones. There are some uncommon ones. Okay, I think now I'm going to do what I'm going to do is I'm going to just show to a whiteboard. Let me see whether I have some slides on that. Okay. Yeah, this may be a good point to start with. So I think this is a solved problem. I think you solved already in the assignment. I have given PF3, right? Right. I gave you this question, I think. Okay. So
Yes.
this is the simplest stuff in heteronuclear NMR. I have a halogen halides of phosphorus, PF3, PCl3, Pi3, PBr3, of which PF3 is the complete I is equal of system both ways. So suppose if I do a phosphorus NMR spectrum of PF3, I will have 3 fluorines coupling with this and giving rise to this. Okay, and then if I will keep exchanging this, okay, the PCl3 will have only one phosphorus signal. I put one fluorine, it will have 2 signals because this is the fluorine coupling to the phosphorus. And then if I introduce 2 fluorines, then I get a triplet. If I put 3 fluorines, I get a quadruplet. Okay, this is how spectrum actually looks like. Okay, pretty much follow the Pascal triangles. I think this is another point I think I want to remind you. All I is equal to off systems follow Pascal's. I is greater than off will give rise to equal intensity. Okay, the intensity ratios. Again, there is a quantum mechanical basis. I'm not going to go into this today. So suppose if you have a triplet involving all I is equal to off, then you will have this Pascal triangles, spectrum. Okay, 1:2:1. But if it is the best example is the CTCl3. How many of you have seen the spectrum of CTCl3? Okay, you seen this, right? The carbon NMR spectrum. 13C is I is equal to half. Deuterium is 2H. Is equal to hello 1. Okay, so the formula we put it, you will get a 2. Okay, Ni plus 1 will be 3 lines. These 3 lines will have the equal intensity 1:1:1. I think only remember this. Okay, that when a quadrupolar nucleus couples, even with the non-quadrupolar one, you will get multiplets of equal intensity, whereas when you have I is equal to half coupling with I is equal to half, you will always have Pascal triangles prescribed intensities in the multiplets. Okay, so that's the first example I thought I will do. Let me just take a new slide.
Professor, at the same time, I was wondering when we are discussing PFCl, chlorine won't be splitting because it is also NMR active, right?
Say it again.
So when we discuss spectra of PFCl2, so chlorine also has this I of 3/2, so it won't be interfering.
Yeah. I mean, so see, what has happened in NMR over the years is that you can selectively, irradiate the nuclei which you don't want. Okay, you can actually decouple all the quadrupolar nuclei. Okay, see, essentially, I mean, sometimes it's better to not look at all the nuclei in a given molecule. Suppose I think you're talking about chloroform, right? What happened to this draw? Okay, let me just take this. Okay, we're talking about chloroform. I take a simple example, chloroform. And CDCl3. So chloroform, the 1s NMR spectrum will be just a singlet, right? There will be a small, very small satellite peak. That's because this will correspond to 99% of the molecules, because the CH3 is nothing but 12CHCl3 99%, 13CHCl3 1%. That's the actual statistical distribution of molecules in solution, right? Now, the 99% has a 12 carbon is a diamagnetic, which not diamagnetic, which is a NMR silent nuclei. So it will not give rise to any coupling, but the 13C will couple with the proton. So 13C couples with the proton, it will give a doublet with the intensity of off and off. So the intensity of this peak is off. This intensity of this peak is off. What happened? Intensity of this peak is off. Each one. But what the NMR baseline is never like this. NMR baseline is like this, right? So there is some noise. So the noise is as good as the 0.5% intensity. Normally you don't see it unless you have very straight baseline. Then you'll have a peak, and then you'll have two small, just spikes. Okay, you see this. That's for CHCl3. Okay. Now, if you go to the CDCl3, the proton NMR spectrum will not give anything, but you can do a deuterium NMR. It's of no interest to us. Okay, but when you do a carbon NMR of this compound, 13C NMR of this compound, this is you have enriched 100% deuterium, so there is no proton at all. So the 13C may be only 1%. The 13C is only 1%, but all these 1% of the molecules will have a deuterium associated with this. So 13C will have always deuterium and never a proton. As a result, the carbon should give one signal. Because deuterium is coupling with that, you will get this. Okay. But now, if you want to complicate your life, then you can also look at the chlorine coupling, because chlorine has several isotopes, and these isotopes have I is greater than half. Some of them have. I think if you go back to the table what I showed you before, chlorine isotopes. Yeah, 35 and 37. These are the abundance. You have this, okay? You have this, 35 and 37 chlorine also, in principle, can couple with this. But what you do is that you actually irradiate. I mean, you ignore. I think he's like, uh, did the Kulkarni talk about irradiation experiments? How you can selectively
Yes,
not
yes.
see them. Okay. So you just, it's kind of a filter. You filter out the chlorines because it's of not interest to us. Okay. So most NMR spectrometers, the modern day spectrometers, have this initial setting itself where you kind of subtract all the background and unwanted nuclei in the beginning itself. So normally in most of the spectra, even if you forget to decouple, this will not show up. If you want only, you have to ask for it. If you don't want, anyway, it's there already. It's taken care. Okay. So I thought that's the answer for the question. Short. What was I doing? I was doing the PCL3, PF3, right? Okay. Now what we'll do is that um, the PF3 was scrambled with the chlorine and got a PF3, PCL3. I do a simple addition reaction. This is a very well-established reaction. A textbook example, way back in 1960s itself, this molecule was made. It's a very simple reaction. PF3 plus ammonia. If you do it under some conditions, you can just simply eliminate one HF and add two NH2s. Okay, so the product what you get is that the phosphorus is bound to two fluorines. One fluorine is gone as HF, one H comes here, and two NH2s come. Okay, obviously this is a P3 compound, trivalent phosphorus. This is a pentavalent phosphorus. This is an addition reaction, a sort of addition reaction. The phosphorus is having a trigonal bipolar geometry, fluorine being the most electronegative, the VSAPR theory and all the things really that will be in the equatorial position. There's one hydrogen which will be in the equatorial. And there are two NH2 groups in the equatorial position. If you look at this particular molecule, it's a very interesting system. It has got these many nuclei in this molecule are I is equal to half systems. All of them are I is equal to half. I have 4 plus 1, 5 hydrogens, 2 fluorines, and 1 phosphorus. In addition, I have 2 nitrogens. As I said, 14 nitrogen is of no use to us. But if I can enrich this into 15 nitrogen, the list gets expanded. The enriching is not such a difficult job. You can easily enrich any sample. Okay, all that you need to do that you have to buy ammonia, which has been enriched with 15. If I can use here 15 nitrogen enriched ammonia, my product will have 15 nitrogen. And if I throw a question like this to you in an assignment or a quiz or an exam, I think you should be able to do. That's all I wanted to know in this course. I think if you can solve this problem, you should be able to solve most of the problem. This is a fairly simple one. I have put here nitrogen. For simplicity, I have made it as a non-quadrupolar. Okay, 14 nitrogen is of no use to me, so I have made it 15 nitrogen. So 15 nitrogen I is equal to half. I think if you have any doubts, I think we just quickly go back to the same table. Oof, 14 nitrogen is quadrupolar. I is equal to 1. If no use to us, creates trouble. But if you go 2 slides back, 15 nitrogen has a very low abundance, but it is I is equal to half. So as what I'm essentially doing here is that I'm enriching my nitrogens with 15 so that I have a perfect all of them. Let me write it slightly better. So essentially you have 5 plus 2, 7 plus 8 plus 2, 10 atoms. All 10 atoms are non-quadrupolar, NMR active, I is equal to half nucleus. If I have to, really look at the spectrum, it's going to be obviously complex. One thing is very clear. I think I can record any of these spectra. I can either study the phosphorus spectrum, or I can study the proton NMR spectrum, or I can study the fluorine spectrum, or I can do a nitrogen spectrum. Okay. Now I'm just going to straight away go and show the spectrum how exactly looks like, and then explain it. This is how the spectrum looks like. Are you able to see this clearly on your screens?
Yes, Professor, we can.
Okay, the bottom is the spectrum. Actually, if I draw a line, this is the spectrum. What you when you record the compound spectrum, this is how it looks like. It's a somewhat intimidating, right? So many lines, looks so complex, but I think it's very fairly easy once you follow the tree diagram at the top. Okay, because as I said, the molecule has a trigonal bipolar geometry. The I'm recording a phosphorus spectrum because phosphorus is central in this. I can also do a proton spectrum. That can be an assignment for you or a homework or even an exam question. Okay, do a fluorine spectrum or a proton spectrum of this compound. But for the time being, we will take phosphorus. So there are 90 lines in all. Actually, there are totally 90 lines in all. How does this happen? Because the hydrogen is the one which is closer to phosphorus in terms of distance as well as the receptivity and all parameters hydrogen scores over fluorine. So the hydrogen couples with the phosphorus first and has a fairly high coupling constant of close to 1000 hertz, about 836 hertz, 1 jph. 1 jph. The 1 jph is about 850 hertz, and you get a doublet. Okay, so that's a spectrum actually. Okay, doublet. Now what happens is that now this doublet is now going to be coupled by the two one bond coupling, that is fluorine, which is strong enough, okay, compared to nitrogen, stronger I would say. So each of these lines are split by the nitrogen fluorine, okay, by two fluorines uh, to the tune of 619 hertz. I'm not talking about positive and negative coupling constants. Let's not really worry about it now. Okay, this is if I do a full NMR course, I can talk about negative coupling constants. But you just only use the mod values or the magnitudes. Don't worry about the signs. Okay, so about 690 hertz. So that gives you a triplet this side and a triplet this side. Since this coupling is almost to the tune of this, there is a crossing. Okay, otherwise they would have had a separate two triplets, but these two triplets cross. So this, and this one set, this, and this is another set. Okay, and now each of these triplets is going to be split into further triplets by the 250 nitrogens. So this 15 nitrogens here is going to split these triplets into further triplets. So all of them go triplet, 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 okay, and triplet. Comes this 4 protons, which are actually the 2-bond coupling. So far what we talked about is 1 JPH, 1 JPF, 1 JPN. Now we are coming to 2 JPH. So this has been expanded here, as you can see. Now each of these, 3 lines get split into a quintet, and then you see some bit of overlap also. So as you can see that 1, 2, 3, 4, 5. This fifth line is overlapped 1, 2, 3, 4, 5. And again 1, 2, 3, 4, 5. Okay, so you see that this is a 15 line. So 15 plus 15 plus 15 plus 15 plus 15 plus 15. 15 into 6 equal to 90 lines. Okay. This, the inorganic spectroscopy is somewhat different from the organic spectrum, because here you have this trees growing. In organic chemistry, the tree doesn't grow so much. If you have an aromatic molecule or aliphatic molecule, after 2 or 3 bonds, the coupling constants become insignificant. But whenever you have a central atom and ligands around it, this chemistry becomes really interesting. Okay. So is this example clear to all of you? If you have any questions, please ask right away. We are not in any hurry to finish something. Hello.
I think it's more or less clear. So,
I will give you the slides. You can have a look at it again. I think next slide actually talks about it. See, this is actually a spectrum. I should show you this first. This is a spectrum first. You can run this animation and then see it yourself. Okay. So when the slide comes to you, you can see this. Okay. Now let me just go back to the whiteboard and then take up another interesting example. This example comes from coordination chemistry. I have tungsten hexacarbonate. The reason I keep coming back again and again to tungsten is that tungsten is I is equal of nucleus. Abundance is about 14.5, or you can say roughly 15%. 15% abundant. Sensitivity is somewhat small, but not insignificant. So tungsten is 183 is the isotope number. 183 tungsten I is equal to of. This makes this example very interesting. Okay, so okay, now a simple chemical reaction. I take this compound and react with PME3. For the time being, I'm doing only 1:1, one carbonyl and one phosphine. I lose one carbon monoxide. If I do a thermolysis, slightly heat it up, one of the CO is relieved, and I will get a compound which is W with the force. So that's my product. This is a beautiful playing ground, for a combined spectroscopy study, because you have a carbon monoxide, I can do infrared, and I have a phosphine, and I have a tungsten. I can do, and I have 13C. Okay, so I have 13C, I have 31P, and I have 183 tungsten. Okay, this is not a complicated molecule. Okay, this is straightforward. Okay, so just to give you how would my tungsten NMR would look like. Tungsten can couple with phosphorus because tungsten is only 15%, as I said, only 15%, but the phosphorus is 100%. So the 15% of molecules in solution will couple with phosphorus because this is my 1J WP. I'm doing a tungsten number. This is tungsten number 183 number. So I will have it. Only 15% of the molecules will take part in the NMR measurement. 85% will not because they are not isotope of nucleus, and I'll have this. Normally, this is about I guess it's about 40 to 100 hertz. I think I could be wrong, a few hertz here and there. Normally, depending on the nucleus, again depending on the other environment. If I do the parallel phosphorus NMR, so I have phosphorus in every molecule, and every phosphorus atom in solution is NMR active because 100% abundance. The T1P is 100% abundant. I is equal to off. Abundance is 100%. The receptivity is fairly good. I think 0.07, if I remember right. So that makes it very easy. So, but only 85% of the molecules in the solution will not have a tungsten corresponding to 183. It's something else. That tungsten will not couple. So, for 85% intensity of my spectrum will have a single line. Now, the tungsten will couple with the rest 15% of the phosphorus giving rise to a doublet. So this is due to 85%. These two peaks combined together 15% are each only 7.5%. This is significant. 7.5% is not something small like 0.5% I talked about carbon NMR satellites. These satellite peaks are quite significant. So you can see that it's roughly about 1:10. Okay, one or I mean less than 1. Okay, I would say 0.9 to 1 to 0.9 to 10 to 0.9, something like that. So you can see the spectrum. So it's clearly this is same as this. So that's an internal check. This is again 1JW, PW rather, 1J PW. But the value, if this is 45 hertz, this also has to be 45 hertz. Okay. Only you are changing the spectroscopy. In one case, you are recording 183W. The other case, you do a 31P. In the case of tungsten NMR, no confusion. All 183 tungsten will have a 31P as a partner. So we'll get simple doublet, move on. Okay. But when it comes to phosphorus NMR, there are two different species swimming in the solution. In one species, you have, phosphorus and tungsten both are NMR active, I is equal to half. In the other species, only phosphorus active. Being the predominant, the only phosphorus active one gives rise to a 85% spectrum, and the less predominant or the less populated the isotopomer, which is the tungsten 183 containing one, gives rise to a doublet, which is because the chemical shift is same. Whether the isotopomer A or isotopomer B, both have the same chemical shift, because the chemical shift for a doublet is always the which is same as the one which is coinciding with the 85% peak. So the chemical shift is same, but one species has a doublet, the other species has this. Is this clear? If it is so, now we'll increase the complexity of the problem a bit more. So this has no, see, this is a simple example. There's no, what I call it as a interpretative value. But now I'm increasing this reaction to two equivalents. I have WCO6. And I'm adding this time 2 times phosphine. So I get WCO4 PME3 2 times. Now I have two possibilities. Now, anybody who knows the answer for the question I'm going to ask can unmute and tell me. What are the spectroscopy techniques which will be useful to identify whether I have a cis or trans? Of course, don't say IR. I think IR is, of course, I've taught already. Now, if I do it, yeah.
How about coupling constant? NMR?
Yes. I'm sorry?
Yeah, coupling constant is what I feel can distinguish.
Yes, because both cis and trans isomers may have a small difference in the chemical shift, but the chemical shift is not good enough, to really say whether you have cis or trans. If you have both, then you can say which is cis, which is trans. Okay. So I'm sure Professor Kulkarni would talked about the trans and cis, right? The coupling constant for the trans ones are always larger than the coupling constant for the cis ones. Okay, so in this case, I think if I have to do, either the tungsten NMR alone or the phosphorus NMR alone might not be some use. So you have to do both. So the tungsten NMR will have now not a doublet like the one what I showed you here, but it will be a triplet. The tungsten NMR will give you a triplet, because the two phosphorus which are equivalent, cis or trans, will couple together, will give rise to. So what I see here is 1JWP. The phosphorus number, on the other hand, there are two phosphorus will couple with the tungsten, right? So yes or no? So two phosphorus will couple with the tungsten, and now the statistics comes into play. Okay, so you have those of you who are taking 438 with me will realize I talked about Si2, S6 as example. I think how many of you recall? I do not know. Where this is a ethane sila analog. Now, now this is 31P. This is 31P. No, I think there's no issue right now here. Okay, so now you will have the 31P spectrum for 80% of the molecule, a single line. Why I drew it so multiple times. Okay, let me draw only once. And now the phosphorus will couple with the tungsten and give rise to a satellite, right? So as Ashwin said, it is going to be the extent of this 1J WP is going to tell you which is really you have in solution, whether you have a cis isomer or a trans isomer. If the WP is larger, then it is actually the trans isomer. If it's smaller, it is a cis isomer. Okay, so it's quite different. 40 hertz in one case, is another hertz in other case. So you can easily say which is cis, which is trans about it. So a further step ahead, we will move to the next example. Without writing the reaction, let me write the product. You have tungsten with 3 phosphates. Of course, you can use IR. I mean, like when I ask a composite question, I may ask you to use both IR and NMR, but here I'm only talking about NMR. So here life is very, very simple. Okay, so let's not worry about tungsten. Could we just put an M also? Now here you have an isomer where 2 phosphorus atoms are trans to each other, and another phosphorus which is trans to carbon monoxide. So clearly you have a 2:1 in a distribution of phosphorus atoms, whereas here this is one off, this is other off, all 3 are equivalent. So you'll have a 3 phosphorus system. This is a 2p 1p system. So you don't have to worry too much about the coupling constants. You can simply say that this phosphorus will couple with these 2 and will give rise to a triplet, right? And these 2 phosphorus will couple with this phosphorus and give a doublet, and the doublet will be twice the size of the triplet. This is due to 2 phosphorus atoms. This is due to 1 phosphorus atom. Center, okay? And this coupling constant is the 2JPP. Whereas here, all 3 are equivalent, and you will get only 1 signal. However, if you want to do this, you can just do the tungsten coupling. So what will happen is that you, apart from these 2 main lines, with the same coupling constants, you will have the satellites here. Same way for this, you will have satellites here. Is this clear?
Sure. So in the 3p case, we are getting only a single peak, right?
Yeah, this is a single. For this component is straightforward, only single. Right. Okay. Yeah, sure. This is a fairly straightforward. So what can then you do? Yeah.
So I think this is how we can distinguish between the FAC and MER isomer as well, right?
Yeah. See, you can use a combination of IR and NMR, but you experiment in the lab, you are there. Okay, you can use either of the two and then be satisfied with one of the two. Okay, in
Right.
an exam, you speak about both, but I think when you do a NMR, I think that's really you know the ultimate proof for this particular case. The next system is even more will be interesting. The next system just you have tungsten with the 4 phosphines, hypothetical system, difficult to make. I have 4 phosphines here and 2 carbon monoxides here. Now, again, extremely easy to use phosphorus NMR spectroscopy because these all 4 are equivalent, right? So you'll get one signal done. And again, IR just one stretching frequency done. Okay, absolutely easy. But here, this is a C2V, so you'll have more vibration frequencies. You know, C2V will come. You're done for water. The same. Okay, you can safely ignore this and only worry about this fragment. You can do IR. NMR, if you come, you know, these two are A type. Okay, these are B type or X type, whatever you write, no problem. Okay, now these two will give rise to a triplet, and these two will give rise to a triplet. You'll have 2 triplets of 1:1 intensity. Okay, right?
Right,
And then
right.
and then your tungsten coupling, which will be different for the cis one compared to the trans one. Okay, if this is for the cis one, you'll have a smaller coupling constant, the satellites. Okay, whereas you'll have satellites for this here. Okay, this tungsten is something which I'm carrying with me because tungsten is also NMR active, but I think it could be molybdenum, then you can forget about that. Okay, and do the thing very easily. Okay, I think pretty much. I think this is one series of examples I wanted to tell you. Okay, how phosphorus NMR can be used. The first series of examples I talked about was um, the example of F2P NS2 twice. The second series was the complexes. Okay, WCO3N 6, I would say 6 minus N PR3 N. If you want to make this problem even more interesting, okay, for example, the first example I will take. The first example is this one, right? Now I can just dig a bit more deep and then bring in my methyl groups also into my discussion. Before I do that, let me just spend a minute on. Remind me to send this whiteboard recording also. I, look at this.
Sure. So before we proceed, can I ask a doubt?
Sure.
So in the just above example, you talked about satellite lines. Where are they arising from? Could you talk about it again?
Okay. So let me just take only that example.
Sure.
I have even here there will be satellite. Okay, even for this will be satellite.
Yeah. Actually, I meant this only. So could you talk where are they arising?
Okay. Now, like the way I wrote for chloroform right now. Okay, I have made this molecule. I take the simple molecule WCO5 PMA3. Okay, the same thing is there for everything. Okay, I'm taking this example. So my phosphorus is 31P is 100% abundant. Tungsten has, let's say, 183 W only 15% abundant. And there is some XW, let's not worry about what it is, 85%, which is of no use to me. Okay, it's not NMR active. Okay, let's say. So if I make a solution of this particular complex, I'll have 2 species in my solution. Species 1 is 85% abundant with the W183 PME3 31P. Okay, and I'll have a 15% abundance of a second species, that is species 2, will have a 183 tungsten I, but you will have a XW and 31 PME3. These are my two different species. The NMR spectrum, but I have in one tube, I have this compound in solution. Both the species are coexisting. I record spectrum. Okay. What am I doing? This is 15%, right? I'm sorry. And this is 85%. Okay.
Yeah,
so this
right.
85% one, which has the X for NMR inactive, NMR silent, will give a phosphorus signal. And there's nothing to couple because this tungsten does not have 183 nucleus. Okay, this is 85% of the molecule. The 15% of the molecule will have a 31P and also a tungsten 183. This is I is equal to half, this I is equal to half. Simple, right? This is just a very simple AX pattern. Okay, same 2Ni plus 1, right? It has to be doublet. Okay, so this doublet combined intensity is 15%. Our individual intensity is 7.5, 7.5. So this is species 2, this is species 1. The observed spectrum is overlap both. If I can kind of cut it, and I move it, and I put it here, that is my observed spectrum, right? Is this clear now?
Yes, Professor, much better.
Okay. Now,
Yeah.
now go to the more complex. It's not a complex, but I just do the other one. W. This example, okay? That's what I think you are a little confusion. This example, right? This example, I'm redoing it. So this is axial. This is equatorial, right? So it's essentially an A2 X2 pattern. You know what is A2 X2 pattern, right? It's a two triplets, right?
Right.
Have you forgotten completely the course of Professor Kulkarni? Okay, I'm sure you done A2 X2 there. Okay.
Yes,
So
yes, yeah.
let's say this is equatorial and this is axial. Okay. The equatorial ones coupled with axial and give a triplet. Okay. So this is essentially axial equatorial coupling, right? J P ax eq, right? Now, again the same thing here. This is assuming all the 100% of the tungsten are NMR inactive, but there exists 15% of the molecules which are NMR active, which is I is equal to half, right? So this won't be 100% abundance. Each of this triplet, they will be reduced to 85% of the abundance. Each one of them is 85%. The rest 15% has to come as corresponding. Oh, sorry, I think I got used an eraser. Corresponding two triplets, which are, so this is 85, this is 7.5, this is 7.5. This is for the axial alone. A corresponding one for equatorial. Is this clear now? I'm still not clear.
Could you repeat the last point, sir?
Why not? God, I'm sorry. There's no confusion up to this, right? So the molecule contains 85% of tungsten not NMR active, but phosphorus NMR active. 15% of tungsten and phosphorus both are simultaneously NMR active, right? Let us now draw the spectrum of both the species separately. Let us not confuse ourselves. This is the right side is a straightforward one. It will give you two triplets. For this one, so this one has got that the axial and equatorial. What will happen is that, let's say now the axial will have equatorial coupling. This will have equatorial axial coupling. And now so instead of having simply two triplets, it will have satellites now. The satellites will be like this. This one is in the middle, leave space, leave space. So bring this and put it here, and bring this and put it here. The total spectrum would be. Is this clear now or not?
Yes, sir. Thank you so much. This is really helpful.
See, the 85% will give simply two triplets. Now tungstenous coupling. So this is the main peak. I'm sorry. What is this? This is these two are the main peaks. These are the main peaks. Now these have to have satellites due to this. The satellites are going to be spaced. How you had a one main peak here and two satellites this way. Same way, each of the triplets will have two minor triplets, okay, which is due to the tungsten coupling. That's all it is, okay. So I may not be drawing it with the equal, it is roughly as I said, 1 is to 10 is to 1, roughly, okay. 1 is to 10 is to 1, the final spectrum. That's the spectrum. Okay, if this is clear, we're already 310. Okay, let me just go to the slides back. I'll just show you a few more examples. So now let me just, before I go to the next example, can I now ask you, do you think you guys can go back and solve this problem? How many of you are confident based on the discussion I had? The fluorines are taken the place of phosphine. That's why I purposely chose the example. Otherwise, the life is exactly same as what it was, right?
Absolutely. But I think here we'll decouple the quadrupole moment from chlorine, right?
Chlorines are to be forgotten. Chlorines are, I assume that chlorines are non-existent. Okay.
Right.
Okay. And then you have to only do the. This will be equal to WCO5 PME3. Okay. Yeah. One point I wanted to discuss and I came off in the middle. Okay. let me just continue that. Okay. Now, you in the meantime, you asked me the question. I got sidetracked. Okay. Now this PME3 is a very interesting system. We only talked about phosphorus, NMR, and forgot the PME3. If you look at it, actually, it's got a carbon and 3 hydrogens, right? So actually, if this itself is a good NMR problem for a 101. Okay, NMR 101, not CH101. For NMR 101 is a good problem. Okay, because here you have 9 protons. I is equal to half. 13 carbons, I is equal to half. And 31p, I is equal to half. 100%, 100%, and 1%. I think this. I probably should have started with this. This itself is an interesting molecule. Now, I think why don't we just write down all the 3 NMR spectra of this compound. The 31p NMR, that's the spectrum. If it's a decouple, if I ignore all the protons, it will give only 1. Suppose if we couple the spectrum, I have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 protons are 1 bond, 2 bond away. So I'll have a 2J pH. 2Na plus 1 would be 10 lines. So this spectrum will become a 10 line spectrum. That will be, I mean, this is not as per the Pascal. I think I probably should draw it a little bit better. I've not drawn it so well. Okay, there is a 10 line spectrum. Okay, the phosphorus NMR. Assume that phosphorus also couples with the carbon. Okay, Ashwardhan, you asked me the question. You have to, carefully listen here. Phosphorus coupled to the carbon. Can it happen? 100% cannot happen. 99% cannot happen. 1% can happen. So each of these peaks should have a carbon satellite corresponding to 0.5%. So it's essentially 10 main lines because 2J pH. And each of the lines are split by carbon only 1%, 20 satellite lines due to 1J PC. So normally this 20 lines you will not see at all. Okay, it will be somewhere in between. But suppose if you have very high concentration of the species and very good resolution, you can see this. Okay, so this is how the phosphorus NMR of this compound would look like. Okay, now how would the proton NMR would look like? Proton NMR is 9 of this will couple with the phosphorus will give a simple doublet. Okay, and this coupling constant and this coupling constant will be same. Okay, because this again is a 2J PC. I'm sorry, not PC, pH. Okay, 2J pH. Okay, this is also 2J pH. That is hydrogen to carbon, carbon to phosphorus. But again, what you should remember is that these lines can also have carbon satellites. Yes or no? You will have it. But as I said, normally the line is so chaotic, so very noisy, this get actually masked. But if you do the carbon NMR, this is 1H. If you do carbon NMR of this compound, now you don't worry about the carbon's abundance because you are only looking at 13. See that 1% of the molecule, you spend more time to record the spectrum, pick up only the 1% of the molecules, 19% of the molecules swimming in solutions are useless for the NMR spectroscopy. Pick up the 1%, but the 1% of the molecules do have 1H and 13p. So they will couple with the both proton and phosphorus. What will the spectrum look like is the homework. Okay, just look at it. Okay. Now, obviously the doublet. I want you to guess whether it couples with the hydrogen first or a phosphorus first. I'm doing a carbon NMR spectrum. One will split it like this. The next one will split it like this. Okay, that's all the spectrum is. Doublet, but you can tell me which couples first. Now I just make this molecule a bit more different, and from a phosphine I make a phosphite. I just slip in an oxygen atom in between. I want you to do the homework, okay, and try to understand how the spectrum would look like. I'm giving you another homework before I move on to something else. Tough? Try it. Not straightforward, but try it. You have two phosphorus centers and you have an ethylene unit, but on one side ethylene unit is directly connected to phosphorus, and the other side is connected through an oxygen. So essentially these two protons become 3 bonds away from this phosphorus as well as 3 bonds away from this phosphorus. Whereas these two protons becomes only 2 bonds away from this phosphorus, but 3 bonds away from this phosphorus. So essentially it's two different molecules actually it is, but this can couple also with this, and this can couple also. So this can couple with this, can couple with that. Try this. I'm not expecting to crack this problem, I think, but it's not too difficult. And in fact, if you carefully search the internet, Google, I think you will find an answer also. Somebody will solve this. Because these are some very elementary problems in proton and phosphorus. I think for all these examples, I think you can assume 13C coupling is non-existent. It's existent, but you can't see it. Okay. Okay, that is almost bringing us towards the end of the course, but I have to show you a few more slides. Let me just discuss.
I feel, sir, the hydrogen H will couple first in the question you gave. Is just what I think.
Since you're trying to answer it right away, let me actually tell you one thing. First, you guys solve this problem. This is much easier. Huh? Solve this problem first. Molecular symmetry. Okay, it's much easier. Then pull out the oxygen and then try to solve it. That's more complex. Solve this. This particular molecule is somewhat more complex than PME3 because PME3 you had CH3 here. It was easy. Molecule is over. But now you have a CH2. And a CH2. So you have to also consider this coupling. Okay, I think you solve this problem. I don't want you to go to the one without oxygen the one side. Okay, what is it telling? I forgot. Oh God.
You're moving to slides as well.
Yeah. I think the slides I'll send you. You can see these examples. This is a nice example, but I think I'm not going to talk about it. Yeah, I wanted to take you directly to the quadrupolar systems. Yeah. How many of you? I showed this spectrum. I think probably in 438. Did I or did I not? Have you seen the spectrum? Any of you recall?
I don't.
I have. I remember. You remember when we shifted from the, the new computer center to the old computer center building. You remember that day also. I remember one day we shifted through the corridor. That day I showed the spectrum. I contextually I remember this. Doesn't matter. This is a spectrum of sodium borohydride. Such a beautiful system. I think if you want to teach, quadrupolar, non-quadrupolar, NMR spectrum, I think this is the best example you can look for. Because I talked about the coordination geometry is tetrahedral. Although boron is quadrupolar, the field is quite spherically symmetric. TD, OH, cubic, okay, all these are considered to be spherically symmetric fields. Okay, As a result, I think the quadrupole effects for any atom which is in the middle of this spherical field is not that much pronounced. Okay, that's kind of cancelled to some extent. So, but however, I told you that there are two NMR active nuclei for boron. There's a boron 10, which is 1/5, and 11 boron, which is 4/5. Okay, so when I is equal to 3 couples, you will have 7 lines. When I is equal to 3/2 couples, you will have 4 lines. Such a beautiful thing, see that? Now, if you take this 1, 2, 3, 4 line, this is a midpoint. And now, that's because 80% of the molecules, again, BH4, 80% of the molecules will have 11 boron, 80%. Let me write on the other side. Boron 10 with the hydrogens. This is 20%. So this 80% of molecules will couple with the 11 boron, which is I is equal to 3, I is equal to 3/2 rather, I is equal to 3/2. As a result, they'll get 4 lines of, I told you the equal intensity. When a quadrupolar nucleus couples with the non-quadrupolar nucleus, you will have a equal intensity, 1 line, 2 lines, 3 lines, and 4 lines. This is the coupling constant, is the 1J 11 boron with the hydrogen. Now, there is a second boron, which is I is equal to 3, that will give 7 lines, but only have 20% abundance. So 1, 2, 3, 4, 5, 6, and 7 lines. You leave these 3 and you leave 3. This is the midpoint. As you can see, the chemical shift is same for both. So this is the midpoint for the BH4, which is coupled with 10 boron, and this is the midpoint, imagine midpoint, which is for 11 boron. So you get a quartet and you get a septet overlapping. So you may take a sodium borohydride from a bottle and put it in the NMR tube and dissolve it and say that I'm dissolving one compound, getting NMR of that one compound, but in practice it is 2 different compounds. It's a BH4, but the isotopomers are different. One is 11 boron, one is 10 boron. 11 boron will give rise to 4 lines which are more intense, and the 10 boron will give rise to a septet, which is 20% divided by 3. So that's about 7%. 20 by 7 is 3%. The intensity of this peak is about 3%. This is about 20%. Okay, so it will be 1 to 7 will be the relative intensity. So these are some very interesting molecules. But my favorite example is this one, germanium H4. So germanium is a quadrupolar nucleus, but in a tetrahedral field. Germanium 73 has an abundance of 8% and I is equal to 9/2. So 9/2, if you put 9/2 here, it will give rise to 10 lines. But the catch here is that only, so I have 2 species, germanium 73 with the 4 hydrogens, 8%, X germanium not NMR active, 92%. So I say roughly 10 and 90. I like rounder of figures. So 10 and 90. So this is the 90 one line spectrum, which goes up, 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 up. Okay, long peak. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 lines is because this 73 germanium couples with the 4 protons equally. Okay, one signal only for hydrogens equally, and 9/2 gives us to 10 lines. So this is 1%, 1%, 1%, 1%, 1%. So you can see that that's why this peak has been kind of taken out of the graph, because he wanted to show the 10 lines. It's such a beautiful example. Can you imagine this? So this is the coupling constant. So this is equally spaced lines. Okay, you will have this 9 spaces in between, all are equal. So the midpoint of is this. So species B gives rise to 10 lines corresponding to 10%, and species A gives rise to 1 line corresponding to 90%. Is this clear?
Um, sure, sir. Sounds
I
better.
just gave you this is more of a teaser. I did not teach anything about quadrupolar nucleus, but I just wanted to give you a feeling for quadrupolar NMR. So I just gave you these two examples. You can find several, because I'm going to give you a slide file, is about 70, 60 slides. You can quickly go through, they're all related to each other. I'm only picking up examples and teaching you here. Yeah, what's the question? Hello.
No, sir. I wasn't asking you.
So what is, this is a famous example. What is the example? This molecule? Ammonia, right? If you take ammonium chloride, this ammonium chloride, NH4, this is again a quadrupolar nucleus, 14 nitrogen. It's not 15 nitrogen. 14 nitrogen is quadrupolar. I is equal to 1. So this is how the spectrum looks like. Okay, but however, you can cool the solution, do some tricks, and then resolve this peak. So it's equal to 1:1:1. It may not look like 1:1:1. These are slightly broader compared to this. So it's roughly 1:1:1 because I is equal to 1 couples with 4 protons, giving rise to this beautiful 3-line spectrum. So this is ammonium plus germanium 4 neutral, BH4 negative. All these 3 molecules have a quadrupolar atom in the middle and a non-quadrupolar proton in the periphery. Spherical field, nice, yeah, 3-line spectrum, equal intensity. 10-line spectrum, like 1 plus 10 line, I would say. And here you have 7 plus 4-line spectrum for this. Okay, so the NMR of these compounds are actually very interesting, and they're very, very, what do you call it, is almost like, I would say, the fingerprint for such molecules. This is like a signature. Okay, one can actually characterize this using. So one example I want to leave you with before I close today, I think it's 3:20. What is the time now?
It's almost about 3:30 now.
Oh, I'm sorry. So I think one example I just want to show you, but not talk about it, but I wanted to go home and see is an example. This is your Si2S6 spectrum. For my 438 students, this may look repetition, but for others it's new. So you have a silicon here and a silicon here, 3 hydrogens. But this is not a quadrupolar, non-quadrupolar. Both are non-quadrupolar. 29 Si, 28 Si, and 30 Si. This is, oh God, 5%. This is negligible, less than 0.25%. And this is 95% roughly. And this molecule can have either 28 or 29. 28 or 29. So it gives rise to a spectrum such as that is shown here. Rankin book has this. And if you open the Rankin book, I think this spectrum has been very nicely explained. I want you to have a look at this. So these slides I sent you by email. Or put it up. This videos,
Yeah.
I think, Ash, you can actually get this video, and then in another half an hour video will be available. Just remind me to put it on the YouTube. I will put it on the YouTube. Slides
Sure.
I will share. And those of you who do not have Rankin book, I think talk to each other and see where it's available. I don't want to give you the link because these
I
are not official sites. These are people have just downloaded and kept it in their sites. I think you can take them and see it. Okay, I have a hard copy. So anyway, so all the best. I think I will come back to you through WhatsApp about the exam. I mean, how it is going to be. I presume that all of you have submitted the assignment, even if you have not submitted it, because you could not understand something. I hope this classes help you to understand. Go back and do the assignment by today, and do it even by today night. I think you will only lose some percentage of marks, but you will get definitely some marks. I think I would say 80%. I would still give you marks if you do the assignment and submit it. Okay, and then I strongly urge you to do the WF6 problem, and that may probably lead you to the exam. Okay, so all the best. If you have any questions, please post it in either in the Teams or in the WhatsApp. I will try to answer all of them. Okay. Anything else before I sign off?
No, sir. Please upload the whiteboard writing also that you did.
Yeah, I'll write whiteboard writing right away. I'm putting it in a few minutes. Okay, bye. Yeah.
Sure.
Okay.
Thank you. Thank you,
Okay.
sir.
Take care. Okay. All the best for all your exams. Not only for this exam, for all the exams. Okay. Yeah.
Yeah,
Bye.
thank you.
Thank you, sir.
Yeah. Bye. Bye.